County, but we're still up there in terms of pressure on healthcare systems. So anyway, that's the status of that. For Wednesday, realize I haven't been referring to your textbook very often, but all the stuff that we've been covering so far has been in your textbook. But specifically for Wednesday, I want you to read chapter 8 through the end of section 8.4. This material deals with doing analysis of variance. So hopefully today we will finish t-tests. We have to go through 2 sample t-tests and paired t-tests, but that won't take us too long. And then on Wednesday, hopefully we'll start doing analysis of variance. So that's what this chapter covers.
Want that reading for next session?
Yeah, for Wednesday. Yep. All right. So we've been through the single sample t-test. This is when you're comparing a sample to some hypothesized value. But then we might also have 2 samples that we want to compare with one another. So this is the 2 sample t-test, and the equations are on the board. But basically, it's just the difference between the 2 means divided by some pooled sample variance. So this, or pooled sample standard deviation. So this is the pooled sample standard deviation estimate. Now remember that when you're doing parametric tests, one of the assumptions is that the variability in your samples is similar enough that you can't tell them apart. And we've discussed the reasons why sample variability being similar is important. And so what a t-test essentially does is it makes that assumption very explicit, and it just forces them to be the same in a sense. And so the formula for this is the square root 1 over sample size 1 plus 1 over sample size 2 multiplied times sample size of 1 minus 1 times the variance of sample 1 plus sample size of sample size 2 minus 1 times the variance of sample 2 divided by the sample size of 1 minus the sample size, or plus the sample size of 2 minus 2. So this is the equation for this pooled estimate of the standard deviation. Look at that equation for a couple of minutes and tell me about some things that you recognize from past work you've done in terms of what the equation is doing. What's the normal standard deviation that you would calculate for a sample you were doing calculations on? How do you calculate the standard deviation? Yeah, it's the square root of the variance, right? So here you have, because this is a pooled standard deviation, you have the square root of variance components, right? Okay, so in this way, you can start to put this in the context of what you already know, which is good. Here, though, we're multiplying the variance times n minus 1. Why would we do that? Why might we do that? Yeah.
Degrees of freedom?
So we have to account for degrees of freedom, but normally in calculating variance, we're dividing by degrees of freedom, not multiplying by degrees of freedom. So in this part of the equation, this section of the equation over here, we're both multiplying times the degrees of freedom times the variance, but then we're also dividing by the degrees of freedom. Why would we do these two things? What's the equation for sample variance? Yep, that's it, right? Look at this equation and look at this portion of this equation, and what do you notice?
We have the n minus 1 and n minus 2.
What's that?
We have the
So you have n minus 1 and n minus 2,
which is the 2.
but that's in the denominator here, right?
They have it in the domain too.
So they also have it in the denominator also. So generally, when we think of the variance, it's essentially the sums of squares divided by the degrees of freedom, right? It's the sum of the squared deviations from the mean divided by the degrees of freedom. It's a general form for thinking about what variance is. So if you're going to do variance, essentially, this is a variance estimate that you're then going to be taking the square root of. So what you need for this variance estimate here is you need the sums of squares in the numerator and the degrees of freedom in the denominator. So the reason that they're multiplying the variance times the degrees of freedom is because when you get rid of that denominator by multiplying both sides times n minus 1, you get n minus 1 times this variance is equal to the sums of the squared deviations. Now, by doing that, you have the sums of the squared deviations of sample 1 plus the sum of the squared deviations of sample 2 divided by the combined degrees of freedom. N minus 1 plus n minus 2 is equal to n1 plus n2 minus 2. N1 minus 1, n2 minus 1 is the same thing as n1 plus n2 minus 1. So this is the combined degrees of freedom. This is the sums of squares of the first sample. This is the sums of squares of the second sample. Sums of squares of the first sample, sums of squares of the second sample, divided by the degrees of freedom. So what you're basically doing is just you're calculating a pooled sample variance estimate here. So another way of writing this equation in a less complicated way is to basically just write it as sums of squares 1 plus sums of squares 2 divided by the degrees of freedom. It means the same thing as this. It's just something that you're already aware of. I told you back when we first covered this, when we were first talking about the variance estimate, I told you that this thing, the sums of the squared deviations of the mean, that this thing is super important. You're going to see it over and over and over and over and over again. You're going to see it in the estimates of t-tests. You're also going to see it in the analysis of variance that we're going to start on Wednesday. This is something that is crucially important. The sum of the squared deviations from the mean. You'll see when you read chapter 8, they're talking about sums of squares this whole time. That's what they're talking about. So this is just another reinforcement of that. So you then multiply that variance estimate times this to get this standard deviation. This whole thing goes here, and then it's just the differences between the two means. So let's say that we have car companies or any manufacturer in the United States, and they're comparing their productivity to Japan. I feel like I did talk about this a little bit last time. Did I or not? No, it must have been in my head, and then we didn't get to it. So we have productivity in the United States and productivity in Japan, especially back in the 70s and 80s. There was a lot of discussion in business about how Japanese automakers in particular were doing a better job than American automakers in terms of their efficiency, et cetera. And people studied this. People in business actually studied this. And one of the arguments they made was that turnover in American companies, American manufacturing facilities, was much higher than it was in Japan. And so they went to various companies, plants in the United States and in Japan, and they measured the turnover rate, how quickly you turn over your workforce in U.S. companies and Japanese companies. Presumably less turnover means that people get to know their jobs better because they're in those jobs longer, and so that might affect quality of manufacturing. And so they got these 5 plants in the U.S., 5 plants in Japan, and looked at turnover rate. So in order to do a t-test to see if these two turnover rates in the US and Japan are different from one another, what do you need to know? Well, you need to know the average turnover in the United States versus Japan, and then you need to know this pooled standard deviation estimate. Well, what do you need to know the pooled standard deviation estimate? All you really need is the sums of squares from the US, the sums of squares from Japan, and the sample sizes for each of these. So the first thing that you need to do is you need to calculate the mean for the US and the mean for Japan. So do that. Who has the mean for the US calculated? Yeah. What do you got?
6.562.
Anybody disagree with that? What about the mean for Japan? Somebody else? 3.118. So for our t-statistic, the numerator we already have 6.562 minus 3.118, and that is 3.444, correct? Is my math right? Okay, so we have the numerator. So now we need the denominator. What do we need to have the denominator calculated? We basically need the sums of squares, right? How do we do sums of squares? Subtract the mean from each of these. We take the square of each of those. And we add them all up. Do we need to divide by n minus 1? No, because all we need is the sums of squares. So do that for that one. Add that all up. That would be your sums of squares for the United States. Do the same thing over here. Square each of those. Add that up, and that would be the sums of squares for Japan. Yeah.
Wait, could you just go back to what the formula was for the overall t-test? And then the S of, I guess, y bar, or I guess x bar.
This is the pooled standard deviation estimate, which is what the denominator is. Yep.
Okay, we're good.
All right. Somebody has sums of squares for the U.S. and Japan. Go ahead and write them up. You have a calculator?
Yeah.
Yeah, go ahead, throw it up there. See if other people agree with you. Anybody else who's finished? Is this what you got for the US and Japan? Sums of squares? So this is just 5 plus 5 minus 2, which would be 8 for the denominator. 1/5 is basically 20%, so 0.2. So this is 0.2 plus 0.2. So this is 0.4 times this whole thing, and then you take the square root of that. So run that calculation on out. This thing is 0.4. This is the sums of squares of Japan, sorry, of the US, which is 0.903. Sums of squares of Japan, rather, and that is 1.932. And then the degrees of freedom is 8. You have to divide this by 8 first, and then multiply it times 0.4. And then you have to take the square root of that. Yep. There should be no negative number. You are correct, but. So that then needs, oh, you did that. So that's square root. All right. Who's got the answer? Yeah. 0.14175. Is that what's inside of here? Square root it, right? Or did you square root it? You square root it? Anybody? Everybody agree with that or not? Okay. So that goes in here. So do that division there, and you will have the value of the t-statistic for this data set. Yeah. Oh, what'd you get? Where? Here? Okay. What did you get, Elizabeth? Okay, so let's look at what went wrong. So what is 7.11 minus 6.562? What? So when you square that, what do you get? 6.06 minus 6.562 squared. Eight minus 6.562 squared. 6.87 minus this squared. 4.77 minus this squared. Okay, and so that sums to this. So what did the rest of you do that didn't get this value? Did you forget to square?
Nah, I divided it at the end, like I was doing
Oh yeah, oh yeah. You don't divide it. You just
Yeah.
need the sums of squares. Okay, so that's the reason. Okay, so this is why I ask you if you agree. When you disagree, you should disagree. So what is the pooled sample variance? What's that? Is that what you got? Oh, you haven't finished. Remember, we're not calculating variance, we're calculating the sums of squares. What's that? I'm wanting to know what the value is of this. This divided by that times that square rooted. Yeah. Okay, so close. That's probably up to rounding. 7705? Okay, that's probably just rounding issues. Okay, this looks more like what I thought it was going to turn out to be. 3.44 divided by 0.77 would be what? 4.469. All right, did you guys all get that in the end? Chris, did you hear that what went wrong?
No, I did not. What went wrong?
Calculating variance rather than sums of squares. When you get the sum, don't divide by the sample size minus 1.
Right.
You're just calculating the sums of squares. All right. So we have this t statistic now, and we have to compare that to the t critical value, which in this case will be at an alpha level of 0.05, and it will be with degrees of freedom equals to 8. And the degrees of freedom you've already calculated, it appears right here. So we can go back to our t-table from before. Now, if our hypothesis is that turnover rate is higher in the United States than it is in Japan, would that be a one-tailed test or a two-tailed test?
One tail.
It would be a one-tailed test because it's directional. If all we want to know is there a difference, what would the test be? It would be two-tailed. So since we're operating under the hypothesis that Japanese companies in the 1970s were more effective than American companies because they have lower turnover rates, we would actually be looking for the one-tailed probability. The one-tailed probability for 8 degrees of freedom is 1.86. And so we would see that the t that we calculated is much greater than the t that is in the table, And so we would conclude that there is a difference. U.S. companies have higher turnover rate than Japanese companies. Now, whether or not this high turnover rate accounts for differences in productivity and things like that is up to, a business person who's doing the interpretation. But the fact of the matter is that there is a difference between these two sets of data. The difference is, about 3.5 percentage points in terms of percent turnover. And so is that 3% significant in terms of affecting productivity and quality, et cetera, et cetera? Well, I don't know. That's, once again, up to some business person to ascertain. But the issue is that 3.5%, 3.4%, that is a significant difference based on these data. Any questions on how that operates? Yes, ma'am. It's normally your degrees of freedom for sample 1 would be N1 minus 1. Normally your degrees of freedom for sample 2 would be N2 minus 1. So the degrees of freedom for both combined is N1 plus N2 minus 2. N1 plus N2 minus 2. In this case, there are 5 observations, 1, 2, 3, 4, 5. So that's 4 plus 4. Or it's 5 plus 5 minus 2. Either way, it doesn't matter. Remember that all of this stuff goes back to the basic fundamentals in statistics. For a given mean, you can calculate a variance estimate. The variance estimate is always the sums of squares divided by the degrees of freedom. So whenever you're combining treatments together, you always have your degrees of freedom adding up. And so another way of writing this is it's the sums of squares divided by the degrees of freedom. So once again, these fundamental ideas you're going to see cropping up over and over again. Questions about how this operates? Yeah.
So for two-tailed tests, you said it would just be general, just like if there's any general change.
Yep, any general change. And all that really changes is the column of the t-table that you look under. So you would look under this column, which is 0.05 for a one-tailed test, versus this column, which is 0.05 for a two-tailed test, in which case that would be 2.306. So you would still evaluate it the same way. It's just this is a one-tailed, whereas t at an alpha of 0.05 degrees of freedom equals 8. Two-tailed would be 2.306, but it still gives you the same qualitative answer.
Is there any difference between the two?
This is just, is there a difference, not is there a directional difference? Yep. In this case, there was a directional difference because the researcher thought, well, U.S. companies have a higher turnover rate than Japanese companies. So also this difference in the numerator, if the U.S. mean had been 3.118 and the Japanese turnover rate was 6.652, this would then be a negative 3.444, and you would certainly reject that because it's going the wrong direction. Not only is it going the wrong direction, it's significantly different in the wrong direction of what the hypothesis was. Yeah.
So anytime there's any type of directionality, we go one-tailed test.
Yep. And strangely, when you read papers in the literature, whether it's in business literature or whether it's the biological literature, physics, whatever it is, oftentimes people just default to a two-tailed test, even though it gains them some statistical power by going with the one-tailed test. With a one-tailed test, your data can be less extreme to find a difference. So anytime you have a directional question, you should test it as if it is a directional question. But people oftentimes just default to a two-tailed test because they're not really thinking about it very well. And sometimes they lose out finding a significant difference that is there um, because they penalize themselves by doing a two-tailed test. The other thing is it's important to think about what the directionality of your question is, because that alters your interpretation of the data. So when you find this difference, it's not just there's a difference. There's a difference, and the difference is the U.S. is bigger than Japan, because that's actually the hypothesis that you tested. And so I always try and get people when I'm consulting on a project with somebody to get them to think about what their question is in the most specific terms, because seldom do people have a non-directional question. Almost always a person walking into a project has some idea of what direction the difference should be based on their knowledge of the system and how it works. If you're an economist and you're looking at inflation data from pre-pandemic to during the pandemic, you have an a priori hypothesis about what direction inflation is going because you have a structural idea that the pandemic is affecting supply chains drives down supply, driving down supply generally drives up cost, the price of things because of simple laws of supply and demand. So you have an a priori directionality to that question. To just test the hypothesis, is inflation different during the pandemic than before the pandemic, you're denying the fact that you already have a good set of solid economic reasons why you would expect inflation to go up during the pandemic. And in the process of not revealing that when you start testing your data, you risk the chance of not seeing the effect of the pandemic on inflation because you test at a more stringent statistical level than you would if you were engaging in a one-tailed test where you think not only is inflation going to change, it's going to be higher during the pandemic. Yeah.
And then you said also, like, when you subtract the two means, it doesn't matter which one's the first.
It doesn't matter, but once again, you would want to do this in a directionality. If your hypothesis is that the US is higher than Japan, you would order it this way because your t-table is expressed in positive terms. If your hypothesis was that Japan is higher than the US, you would have flipped those so that once again the resulting t statistic is consistent with your hypothesis.
But regardless, when you compare the t-statistic to the table value, you compare it in absolute value.
Yeah, but once again, you need to make sure that the directionality of your hypothesis is incorporated in your interpretation of the result. Regardless, so we could have done this arbitrarily. We could have done it arbitrarily. The Japanese rate minus the 652 minus the US, that would have made this negative. But then we would have had to have known that that's negative because we put Japan before the US, and that negative really represents that the US has a higher turnover rate than Japan does. So once again, knowing what the question is ensures that you can interpret the result correctly. Yeah, you're never gonna find a t table that is expressed in negative terms. It's just that if you have a hypothesis that dictates that the t be negative, you basically evaluate the positive, and then you just know that it's on that side of the distribution, the negative side of the distribution. Other questions? And this is why it's crucially important that you understand what the question is that either you're asking or that the researcher that you're working with is asking, because that then influences how you interpret things. All right, other questions? Okay, the last thing that we want to do is we want to deal with paired t-tests. Remember that one of the assumptions of doing basic parametric statistics is the independence of the data, but there are times that you want your data to be not independent, and you want them to be not independent for perfectly good reasons. And we had a biology student years and years ago who was doing a senior thesis project. She was really into CrossFit, and she was interested in whether or not CrossFit actually improved one's performance. And so she got some people to participate in this study where she put them on CrossFit for 6 weeks, had a control group where she didn't have them on CrossFit for 6 weeks, and then she conducted what basically was a two-sample t-test. CrossFit people versus non-CrossFit people. But of course, the problem with that is that there's variation within the individual that is important. So she's not just interested in variation between the two samples. Do you guys have a question that I can perhaps answer?
I was just asking a question.
Yeah, what do you got?
I was
Ask me the
just talking
question.
about single-tailed.
Oh, single-tailed versus two-tailed?
Yeah. It
Okay.
was not that important.
It can be that important. What's your question?
I was just asking what the equation was because I haven't written that.
For,
Single-tailed.
or single sample? Single sample or single tail?
Uh,
Because that's a single sample t-test.
then I mean single.
Yeah,
sample.
okay, all right, okay. And I think I have that. Is that in the PowerPoint? No, I don't have it in there. I should add that. Okay. So in this CrossFit example, the individual matters because what you're doing is you're taking individual one, you're measuring them at the beginning of the study, and then you're measuring them again after 6 weeks with CrossFit. And so there may be variation that is inherent to the individual that is important. And so you don't want to compare this set of individuals with this set of data, assuming independence, because they're not actually independent. You actually want to compare what is the performance of this individual at time 1 and what is the performance of this individual at time 2. And so what we do is we explicitly recognize that in the calculation of a t-test. And this gets to your question about a one-sample t-test. This is essentially a one-sample t-test, but the sample data that you're looking at isn't the raw data, it's actually the differences. So what you do is you take the difference. So this is a data set where you're looking at weight gain or loss after a person undergoes a dietary modification. So we put you on a diet and then we see whether or not you have lost weight or not. So this is the weight that you started at. This is the weight that you ended at. What you do is you calculate the difference. Then that keeps those two data points linked through the difference. And then what you do is you essentially do a one sample t-test, which if you recall the equation for a one sample t-test, it's simply the difference between the means divided by, well, one sample t-test, y1 minus whatever your hypothesized value is, divided by the standard error of the mean. And so this is the one sample t-test equivalent, yeah.
Is that a 0 up there? Or is
This is a 0. So it could be any value. You could be testing against, maybe your hypothesis was that those differences should be 5 pounds. You wanted to know whether people gained or lost 5 pounds or less. And so this could be whatever, this is whatever the hypothesized value is that you're thinking of. So once again, it all depends on your question, but generally the form is for a single sample t-test, what is the difference between what you observed and what your hypothesized value is divided by the standard error of the mean of your sample. And so that's the same way here. The only difference is that this is the average difference divided by the standard error of the difference, whatever that is. So in this case, we have to do all the same calculations that we've done before. So we have 150, 143, we have 195 to 190, we have 188 to 185, 197 to 191, and 204 to 200. So what we're interested in is the amount of weight loss. So this would be 7 pounds lost there, 5 pounds lost there, 3 pounds lost here, 6 pounds lost there, and 4 pounds lost there. These are the differences. So now what we need is we need the average difference, and we need the standard error of the differences. So get calculating.
So in this case, we're hypothesizing that
They didn't lose any weight. Yep. Once again, because you're looking at the difference between an individual at one time point and another time point, oftentimes you're testing against the hypothesis of no change. But you could easily hypothesize against a hypothesis of some degree of change. And that would take the place of 0 in that case. But when you see it in a textbook, it's usually listed as 0. Is my math correct so far? Somebody will have to give me the square root of 2.5 because I can't do square roots in my head. And the standard error is 1.581 divided by the square root of 5. So the t-statistic is the average difference, which is 5, minus a hypothesized difference of no weight loss whatsoever, divided by 0.707. That ends up being so that's your t-statistic that is observed. Now you're going to calculate, you're going to look at the table to find the t-statistic that corresponds to this particular data set. What would that be? What's that? 2.132. Why did you choose a one-tailed test? Who was that? Yeah, why'd you choose one-tailed test? You don't care if they gain weight. Yeah, exactly. You care if they lost weight, so this would make it a one-tailed test. And so we compare this against alpha of 0.05. Degrees of freedom equals 4, 1 minus the sample size, and this is a one-tailed test. So that would be 2.132. So did these guys lose weight? Yeah, they lost weight. It was only an average of 5 pounds, but it's detectable. And part of the reason that it is detectable is because you maintained the identity of the individuals and kept those data linked. The two heaviest people to begin with, what was their overall loss relative to kind of the average loss? So this person lost quite a lot. This person lost quite a lot. This person lost quite a lot. This person lost somewhat. But relative to the average, they really didn't lose very much. And it may be that they didn't lose very much relative to the average weight loss simply because they started out at a heavier weight to begin with. And so keeping that, maintaining those data as linked is important in finding these differences. That's how you do a paired test. So I'm going to post a homework assignment on t-test. I'm going to be quite honest with you. I have never in my career actually done a t-test for real because I just generally work with data that are more complicated than this. I actually have a student right now who has a t-test that needs to be done. That's the first time that I've ever done a t-test on real data that isn't from a book. And it turns out that it's a paired t-test. He's looking at individuals. He's interested in geckos. He's looking at individuals that are carrying eggs. So he has females that he catches in the field that are what we call gravid, which means that they have eggs. You can see the eggs in their abdomen. You can just turn them over and you can see the eggs actually through the ventral body wall. They show up as white. And then he weighs them and he races them down a racetrack to see how fast they run. And then after they lay their eggs, he weighs them again and he races them again. Because presumably after a gecko loses its eggs, it's lost a bunch of weight. And because it's lost all of that weight that they're carrying around, all that extra weight that they're carrying around, what are they probably doing? They're probably running faster. So he has a hypothesis that wants to see if the weight at this stage is greater than the weight at this stage, and if as a result of that, the speed at this stage is actually less than the speed at this stage. Because each individual is being measured before they drop their eggs and after they drop their eggs. Would this be a single sample t-test? Would this be a two-sample t-test? Or would this be a paired t-test? Be a paired t-test. Is this a one-tailed test or a two-tailed test? It's one-tail test because he's actually interested in a particular directionality. So you won't find yourself doing these types of tests very often because in the real world, people oftentimes bring you much more complicated data than a simple two-sample test. But occasionally you do run across times when you need to do them, and then you need to drudge up that memory of how you go about doing them. Yeah.
So we can't do a two-sample test here because
They're related to one another.
right.
This is the weight of female 1 versus the weight of female 1, and the speed of female 1 versus the speed of female 1. Yep. All right. We will start tackling analysis of variance on Wednesday.